computer. There we go. Okay, so the first thing is to notice that, or is to remember that the speed of light is, let's see, can you see this screen? I'm a little worried that it doesn't look as though, it doesn't obviously show that it's being, that this is the screen that I'm sharing. Can you see something that says examples for chapter 12?
Yes.
Okay. All right, good. Thank you. And let me put this over there also. So one thing that what we learned from the cosmic microwave background radiation is that the Earth is moving at about 1% of the speed of light in the direction of the constellation Leo. Actually, since I'm not an astronomer, I have no idea which way.
Is that with the galaxy?
Constellation Leo. I'm talking about the planet Earth. Now, the planet Earth, of course, is going around the sun. The sun is going, flowing with the galaxy, and the galaxy is moving. So it's a and probably our galaxy is moving in a group of galaxies, and that group of galaxies is moving, and all of space is expanding. So all of this is the net motion of Earth relative to the cosmic microwave background is 370 kilometers per second, which is a little over 1% of the speed of light. And so the cosmic microwave background would look like this, looks like this in the Earth's frame, but when you take out the Doppler shift induced by the velocity of the Earth, then this is the picture of the cosmic microwave background. As you know, the average temperature is around 2.7 degrees Kelvin, and it's a remarkably in its rest frame, the CMB is remarkably homogeneous and isotropic. And that's good to 1 part in 10 to the 4th. The inhomogeneities, which are colored here, red and blue, are roughly parts in 10 to the 5th in temperature and or intensity. And by the way, this gray thing, this gray outline is the outline of our galaxy, the Milky Way. Now, Michelson-Morley, over 100 years ago, did an experiment that showed that the speed of light is independent of direction. And at that time, of course, they knew that the Earth was moving around the sun and at a good clip, and that the surface of the Earth rotates at about 1,000 miles an hour.
With the Michelson-Morley, didn't they detect a 1/40 signal?
I'm sorry, I didn't quite understand what you said.
The Michelson-Morley experiment, didn't it show a null result by 40 degrees of magnitude? It was 1/40th of the signal, too small to have an ether.
Let's see, I still don't quite I'm a little hard of hearing, but
the difference in the fringes when we went through one season. The Michelson-Morley experiment.
I still don't understand, but the Michelson-Morley experiment was, it showed that the speed of light was independent of direction. And when you realize that the Earth is moving at 1% of the speed of light, and you see that Michelson-Morley got had a null result, that shows that the speed of light is really independent of velocity. Of course, we can do a lot better today than the Michelson-Morley experiment. And what Einstein did in special relativity was he said, among other things, he said that he interpreted that as saying that electrodynamics is the same in any inertial frame. So if you have any laboratory that's moving at a constant velocity relative to the CMB, although he didn't say it that way, relative to the CMB, that would, excuse me, that would, the electrodynamics would look the same, no matter how fast or in what direction your laboratory was moving, as long as the velocity was constant. Einstein later, about 10 or 15 years after that, generalized it to general relativity. And what he formulated it as was the principle of equivalence. And this says that, here, let me see if I can make this bigger so that it's easier to read. The principle of equivalence says that in any gravitational field, one may choose free fall coordinates in which all physical laws take the same form as in special relativity, without acceleration or gravitation, at least over a suitably small volume of space-time. Within this volume and in these coordinates, things behave as they would at rest, deep in empty space, far from any matter or energy. The volume must be small enough so that the gravitational field is constant throughout it. Such free-fall coordinate systems are called local inertial frames or local Lorentz frames. And what's happening in any of these frames is that electrodynamics looks the same as in a laboratory that's not moving at all. So let me say a little more about these things. What Einstein, well, actually it was somebody else, I think it was Lorentz or maybe Poincaré, who realized that the equations of electrodynamics looked the same if you transformed your space-time coordinates in this way. Let me make this also bigger so that it's easier to read. So this is called a Lorentz transformation. This is a 4x4 matrix, an example of a Lorentz transformation, say in the one direction, the x direction, say. It would look like this: cosh, sinh, cosh, and then just the 2x2 identity matrix. And it would look like this: x0 prime. This is x0 is c times t, the speed of light times the time. So it's essentially the time, is cosh theta x0 plus sinh theta x1. And then x1 is what I would ordinarily call x, x2 would be y, x3 would be z. But anyway, x1 prime is sinh theta x0 plus cosh theta x1. So that's a Lorentz transformation in the one direction. And a point x0, x1, x2, x3 in the primed in the
isn't the transpose equal to itself for that matrix?
Actually, you know what? This equation is wrong. There shouldn't be primes on this. What was your question?
Isn't the transpose equal to itself?
I'm really having trouble.
Oh,
yeah, well, in this particular case, L transpose is L, yes.
Oh, okay, because I was going to say, why do you write transpose?
Yeah, well, it's, in general, it's L. If you have a rotation, it's not, you don't get, for rotations, the transposition has an effect.
Okay.
And here, I shouldn't have had primes on this, so I need to fix equation 1210. That's too bad because that's in the published version. Anyway, one thing that's invariant here is the inner product of the inner product of any two 4 vectors. This, since we have 4 coordinates, the basic thing we think about at first in special relativity is things that have 4 components, and we call them 4 vectors. If they transform this way under Lorentz transformations, or if that's the way the coordinates look when you compare coordinates in 2 different inertial frames. This infinitesimal distance between 2 points that are separated by dxi, say, this is dxi, eta ik, dxk. When you have an upper index and a lower index that are the same, that means you sum over I from 0 to 3, and here you sum over k from 0 to 3. That's the summation convention, which I'm defined here. This was something Einstein introduced more than 100 years ago, and he just got tired of writing this sum symbol. This distance is the physical distance, and because it's physical, it's invariant under, it's the same in any coordinate system, at least if you use sensible coordinates.
But why does physicality require invariance?
Well, the way I think of it is, if something's physical, then it's real, and you can use any coordinates to describe it, and
Like a conservation law?
you get the same thing. Now, that's actually only true in general relativity, where instead of eta ik, you have gik. But in special relativity, it's true as long as the set of coordinates you use are those for an inertial frame.
Oh, okay.
And or an inertial frame under a Lorentz transformation. Anyhow, so in order to have this thing invariant, what you've got to have is, well, the dxi's are given by L times the dx's, and the dx prime k's are LKJ, dxj. So you have that this is equal to that. And that tells you then that LIL, eta IK, LKJ has to be LJ, eta LJ.
Are we going to get to the Christopherson symbols this semester?
Say it again.
Are we going to get to the Christopherson symbol this semester?
Yeah. Don't worry. By the way, Alex has a perfect right to talk as much as she wants and to ask all the questions she wants. Okay, so.
Of course, thank you. I'm just taking it all in right now.
Okay, I like your dog. I have a dog too. His name is Sam.
Thank you. I've got 3. That one in the picture is Rogue.
My brother's name is Alex.
I see. All right, so let me so let's see what so not only are the dxi's dotted into each other with an eta here, that's invariant, but also the inner product of any two, the dot product of any two 4 vectors is invariant. And an example of that is, suppose P and Q are the 4 vectors representing 2 events. Then if the Lorentz invariant dot product is the space part squared minus the difference in the time part squared. by space part, I meant P minus Q. This is the dot product of the 3-vector P with the 3-vector Q, the space part of the 4-vector P, space part of the 4-vector Q squared minus P0 minus Q0 squared. If that's positive, we say it's space-like, and the points and the separation delta S is called the proper distance between the two points. And space-like events, because the space part is the main thing that separates the two events, there's some Lorentz frame in which these events P and Q occur at the same time in some Lorentz frames. And
isn't that if the inertial frame undergoes proper time?
I didn't understand that.
Sorry, actually, that question didn't make any sense. Never mind.
By the way, we have a chat function. If you want to ask questions, you can also bring up chat. I don't see where. Let's see if I can get a chat thing going here. Chat. Okay. So anybody who wants to ask a question can also type it in as well as saying it. So space-like, 2 points are said to be space-like if their difference is a space-like 4-vector. If, on the other hand, it's a time-like 4-vector, that is to say that the time difference is more important than the space difference, then they're said to be time-like. And time-like events occur at the same place in some Lorentz frames. Now, light-like points, these are points, of course, where the delta S squared is just 0 because the space part squared is the same as the time part squared in size. I was using upper indexes for the coordinates. X0 is C times T, and X1, 2, 3 is the 3 components of the space vector X. We say those transform contravariantly, which is an awfully big word. And what we mean by that is that they go this way under a Lorentz transformation. In other words, they transform just as you just multiply you just write X prime equals matrix L times vector X. On the other hand, the derivatives are a little bit more confusing. The derivatives I write, and most people write with lower indexes or indices. The partial derivative in the X0 direction or the time direction is the partial derivative, and mathematically it's the derivative with respect to X up a 0. And these are said to have lower indices and to transform covariantly. And if X prime is Lx, then X is L inverse X prime. And if you then use the chain rule, you can see that d by dx prime j, say, is d by dxl summed over L times dx, the partial of xl with respect to xj prime. This thing here is, using this expression, we see that's just L inverse Lj. And let's see, on an earlier, we'll maybe go back here and I'll just mention some of the mathematics here. What we saw here is that the definition of a Lorentz transformation is this expression here. Now this L here, IL, is, if we want to have it Li, we'd write it as the transpose. So it's L transpose eta L is eta. That's what this is in matrix notation. And so actually, to avoid, so we can write it this way. In other words, L inverse is eta L eta, or equivalently eta L transpose eta. But the transpose, when we write L transpose, we have the K on the left and the I on the right. To avoid having lots of eta matrices, people define this to be that. And then one can write, let me skip ahead. I was actually editing that this afternoon and I got distracted, actually by an Instacart delivery. One can then rewrite L inverse as simply L sub j eta, L sub j upper L. The idea here is that to avoid having all the etas, when we have a sum over K, say here, with an eta, what we interpret that as just raising the K. And then when we have a sum over I, we interpret that as just lowering the I. And so that becomes, the K becomes an upper L and the I becomes a lower J. So this is a neater way of, or at least a simpler way of writing L inverse, the inverse matrix. I'm going to, after class, I'm going to straighten this out and correct that mistake. And I'll put the new version on the class webpage.
Will the examples PDF also be on the class webpage?
Yes, and let me tell you, what happened was I normally had been using an Office iMac, my Office iMac, to host the class web pages of the courses I teach. But then there was an electrical surge in the physics building and it wiped out the hard drives of both of my iMacs. And because of the pandemic, I just didn't do anything. I only got one of them fixed last week. And so there is a new, let me give you people the addresses of the Office iMacs. And the easiest way to do that probably is for me to go to bring this directory up here, and now just to go to, right, short course on relativity. Here's the web address up there on top, the web address of the new class web page. It's quantum.phys.unm.edu/relativity, and then a slash. I don't think the final slash is needed, but anyway, it's quantum.phys.unm.edu. Let me see if I can copy that and stick it in the chat. No, I can't. Oh wait, type it here, hold on. Yeah, there it is. Can you see that? There.
Yeah, perfect.
Okay, so that's the place to go for the class webpage. So let's see, I'll move this out of the way then. So I'll have the notes for chapters 13 and 14. Well, I'm not going to adjust 14 at the moment, but for 13, I'll put them on the webpage. I'll update the webpage tonight. So let's see. The partial derivatives look like this. The partial with respect to xj prime is then this here. And in fact, I'm going to write this more simple. Yeah, I'm going to write this more simply using this relation, and I'll edit that tonight and put it up on the screen on the web page. Now, particles, a particle moving at speed v. You see, the thing that's invariant here is this ds squared, and it's invariant under Lorentz transformations. And it's if dx is the position of a particle moving at velocity v, then this is v squared minus c squared times dt squared, because dx is v dt. And this delta tau squared is just defined to be minus delta s squared. Oh, let me just accept and tell I can't talk. I can't talk now, I'm teaching. So here, delta tau squared then, which is minus delta ds squared over c squared, is then this thing with a minus sign. So it's, and if you divide by c squared, you get a 1 here. So it's 1 minus v squared over c squared dt squared. So you see delta tau squared is always less than delta dt squared. And so the proper time is smaller than the laboratory time. And I hope you guys have seen that marvelous movie, Interstellar, I think it was called. Is that the right name? The one that...
Is that where it falls into a black hole and finds the past?
Right, it's the one where they did the physics correctly because they had various, they had Thorpe, I think, or...
Yeah, they tipped Thorne, but I mean, I think he used a block sphere.
Yeah. Well, anyway, I highly recommend that movie to anybody doing physics or astrophysics or astronomy. One of the things in it is that the people who go off in the spaceship to a planet near a black hole, because of the gravitational field of the black hole, their proper time is vastly slower than the lab time on Earth. And so when they get back to Earth, the people they knew as young people are now my age.
Yeah, so doesn't he meet his daughter and she's older than him? She's like,
and well, let's not, if Alex hasn't seen it, let's not.
I haven't seen it, but it's on my to watch list, first of all because I find it interesting, but also I am an astrophysics major, and in the astronomy course the final project is to watch movies and talk about what they got right in terms of astrophysics and what they got wrong in terms of astrophysics. And that's one of the options to watch.
Yeah, that's the one to watch, because all the others got everything wrong, but this one got almost everything right. The part they didn't get right, I might as well just tell you, give you a leg up on that course. The part that I know that they didn't get right is when they were going through some gravitational field, and there was all sorts of vibration and so on and so forth. That's actually wouldn't happen. It would be a very quiet trip through the, in fact, they would be in an inertial frame, for a free fall frame. The ship would be in a free fall frame, so there wouldn't be any vibration or noise at all, but they couldn't get the director to agree to that. And so they just gave in and let the director put in the sound effects and the special effects and so forth.
Does it have to be a Schwarzschild black hole to be a smooth ride?
Again, I'm a little hard of hearing. I didn't quite understand. Maybe if you use chat, I can. I can read what you type rather than, because maybe your microphone isn't very good.
My microphone is not very good, so I'll type it.
Yeah, type it in. It'd be easier. Anyway, so in the lab frame, the time that's the proper time divided by this smaller number is the lab time. And so this is why the people on Earth seemed, well, were much older than the astronauts who had been. You see, a gravitational field has a similar effect to moving at a high speed. We'll see that in a few weeks, or a couple of weeks, actually. One striking example of time dilation is muon decay. A muon at rest decays in 2 microseconds. And on the other hand, it takes a muon created in the upper atmosphere 30 microseconds, 33 microseconds to get to the ground. And hardly any would get to the ground if it weren't for the effect of time dilation. And if the muon I worked it out this way to make the numbers simple. Some of the numbers simple. If the energy of the muon is around 750 MeV, million electron volts, then this factor is about 7. And so then the probability of the muon reaching the ground is 12%. And that's an increase of 460,000, an increase by a factor of 460,000. Now, why don't I do some kinematics here? The thing that students should keep their eyes on is things that are invariant, because they're very simple. They're the same in all Lorentz frames. And one invariant is ds squared or dTOR squared, and that's this square root here. And so if you take a 4 vector and you divide it by something that's invariant, you get another 4 vector. And this is called the I guess the proper velocity or something. Anyway, so you take x0 and x, you divide by time, and then you multiply by dt over dTOR, and dt over dTOR. Oh, I left out a dt here. That's another mistake. So 12.3. Actually, this is something I edited this afternoon, so it hasn't been published wrong. Anyway, dt dTOR is 1 over this square root. And this, of course, is c and v. And so this is, I don't know what people call this. I guess a proper velocity might be a good way to call, a good name for it. In any event, if you multiply it by m, what you get is the energy momentum 4 vector. So you've had this x is itself a 4 vector. You divide it by a scalar and you have another 4 vector, and this is the 4 momentum. And so the ith component of the 4 momentum is m times the ith component of u, which is dxi dTOR. And writing this all out, it's this expression here times m. And now you see Einstein's equals m squared, c squared relation here, that the energy here is an m over this square root times c, and then a v here. So this is then the energy momentum 4 vector. And its invariant inner product, of course, is a constant. And that inner product is just c squared p squared minus e squared, and that's minus the square of the mass times c to the fourth. So that's an invariant. But the inner product of any two four vectors is an invariant. When I say inner product, I mean the inner product with one index up, one index down. And what that means is that you take the dot product of the space parts and you subtract the product of the time parts. And that gives you this quantity for any two four vectors. The time dilation factor turns out to be the ratio of the energy to Einstein's formula for the rest energy. And the velocity of a particle is its momentum divided by its equivalent mass. So V is P over E divided by C squared. And I should have had another, I should have put a right-hand side, I think, to this equation. I think I'll do that tonight, clarify it a little bit. The analog of Newton's law, F equals ma, is, well, what we want is a four vector on the left-hand side. So we differentiate twice with respect to the proper time, not the ordinary time, because the proper time is an invariant. So then that's m dui dTau, or it's equivalently dpi dTau, and we call that the four vector force. And so what about time dilation and proper time? Here, if you have a particle of mass m, full momentum p lab, it travels a distance L in time t, the displacement is that. In its own rest frame, the particle's full momentum and displacement are just this and that. Since the Minkowski inner product of two four vectors is invariant, this in the rest frame is this in the lab. So we have the rest frame looks this way, and that's equal to minus mc squared tau, and tau is t times this thing. And so I guess I've made that too long description, but anyway, the phase of a particle, you know, is for a plane wave, it's e to the I p dot x over h bar. And so this is actually minus I mc squared tau over h bar. So this mysterious factor that occurs throughout quantum mechanics is actually just the proper time. I think that's interesting, and I haven't seen it emphasized in books on quantum mechanics, but it's true. So that phase factor is the proper time of the particle there. As I said, the use of invariance really makes things simpler. And so back, I must be 50 or 60 or 70, maybe even 80 years ago, people at physicists at Berkeley wanted to know how big an accelerator they'd have to build in order to create an antiproton. And so the reaction they wanted was P plus P goes to 3P plus P bar, the antiproton. And so the conservation of energy momentum, the energy momentum four vector gives you P plus P0 is the proton at rest, one of these protons, is 3P prime plus P bar prime. Here I'm assuming that the momenta of the three protons is exactly the same. So I'm going to make the calculation simple, I'm going to set Siegel to 1 and use this equality in the invariant form. P plus P0 squared is in the four vector sense of the invariant dot product of that squared is 3P prime plus P bar prime squared. And so now if you multiply out, these are all four vector inner products, you get P squared plus P0 squared plus 2P dot P0. Well, P P squared is minus the mass of the proton squared. P0 squared is minus the mass of the proton squared. So you just have 2 P dot P0. But P0 is just, because it's at rest, it's M0. And so this is altogether minus 2 M proton squared minus 2 E proton M proton. Now, if you compute this in the frame in which each of the 3 protons and the antiproton has 0 spatial momentum. So that's the threshold process. In other words, you smash the two protons together, and then you look in the rest frame in which there's the least amount of kinetic energy, and that's where all the 3 protons and the antiproton, all have momentum 0. And in that case, what you've got is 4m0 squared. That's minus 16. And so now if you equate minus 16 to this, you find that E has to be 7 times the mass of the proton. And so 6 mass of the proton is the kinetic energy, the threshold kinetic energy of the proton, in order to have the process go. And in 1955, when the group led by Chamberlain and Segre discovered the antiproton, the nominal maximum energy of the protons in what they called the bevitron was 6.2 GeV. So GeV were called BeV in the United States in those days. The Europeans then, BeV stood for billion electron volts, and the Europeans said, well, we don't want that. We want to call them GeV. I think the English objected because they used billion for something else. So we finally get to electrodynamics, and this section is just a review of standard electrodynamics in the kind of units that most people use, MKSA, or standard international units. And in those units, the 4 vector is minus the electrostatic potential over C times the 3 vector potential. Well, I wrote that with a lower index. I don't know why the hell I did that. That was stupid. 12.31. In other words, the much simpler equation is A upper I is phi over C times A. Anyway, the magnetic induction is, of course, the curl of A.
Yeah, you put it as negative. That's that's what happens when you move.
Oh, I'm sorry. You wrote a question here. Does the black hole have to be a Schwarzschild? To tell you the truth, I don't actually remember the movie well enough. What I remember is I was at a lecture, or I heard the Caltech physicist, I think it was Thorpe, but I'm not sure.
Yeah, it's Kip Thorne, yeah.
Anyway, was it Kip Thorne?
Yeah, yeah.
Okay. Well, anyway, I heard Kip Thorne say that the bolting and the thing should have been very peaceful and like free fall frame, but I don't remember enough of the movie to know what they were what the movie scene was.
Yeah, but so isn't the lower index for A, isn't that the negative of, or that's the contravariant?
Well, yeah. All right. Let me just mention about this. You raise a good point here. In special relativity, when you raise or lower an index, you don't have, that has no effect on the 3 spatial components, and it just flips the sign of the time component. So this whole business is pretty trivial. And I should have written this equation with an upper index, and then I wouldn't have had a minus sign, and then I could have had here A lower I is equal to this. I don't know why I wrote it that way. Anyway, the curl, the ith component of the curl is epsilon ijk, the partial derivative with respect to xj times ak, and here we're just summing from 1 to 3. And okay, right. And epsilon ijk, this is this totally antisymmetric tensor in which epsilon 1, 2, 3 is 1. So epsilon 2, 1, 3 is -1, and so forth. Anyway, this is just ordinary electrodynamics. The electric field is the minus the time derivative, minus the gradient of the electrostatic potential, minus the time derivative of the vector potential. So one way to write it is this way, where dot means time derivative. Now, a nice way of writing these things is in terms of the Faraday field strength tensor. So then you say partial A lower j, partial xi minus partial A lower I, partial xj. Now here, I and j are going from 0 to 3 because this is a 4 by 4 matrix, and it's anti-symmetric. As you can see, if you interchange I and j, you get a minus sign. And the electric field then is C times Fi0. Magnetic field is an epsilon multiplied into the Faraday tensor, or it looks like this. Or a simpler way of writing it is that it's just the curl of A. And the 1/2 takes into account that this gives you the curl of A, but so does this.
What is A again?
What?
What is A?
What is A? You know, if you type, it'd be so much easier.
Yeah, these things are hard to type. Okay, I'll type it.
Yeah, everything is muffled when you talk. Anyway, the inverse equation here, F being epsilon B, that arises from this little derivation here, which I don't know, it's, I think it's easier for you to sort of puzzle through it than for me to type it. What is A? A is either the 4 vector electrostatic potential over C, and then 3 vector A, or it's equivalently just the 3 vector A. So it depends on, I mean, there are two, A stands for two different things in electrodynamics, either the space part of this 4 vector or the whole 4 vector. In elementary electrodynamics, one typically talks about 3 vector A, and then one talks first about the electrostatic potential and then introduces the 3 vector A. And then if one does special relativity, one combines them like this into a 4 vector. So now let's look at Maxwell's equations. There are 4 of them, and 2 of them are called the homogeneous equations because they're just something equals 0. And they're the same in vacuum and in matter. Whereas the other 2 are said to be inhomogeneous because they have source terms, the free charge density and the free current density, and then something called the this is, I think, called the electric displacement D. So let's see, we're actually out of time. In fact, I've run 4 minutes over, and I don't like to keep students longer than they should be. I will touch up these notes and put them on the class webpage, and I'll and I would, you know, urge you to, well, Alex, I would urge you to ask more questions, and if you have them. And
Okay.
I mean, just, you know, you learn more by asking questions. In fact, the other day, in fact, yesterday, I sent email to a professor at Columbia asking him 2 questions about a paper he wrote some years ago. And he answered me this morning at the crack of dawn by email. So I learned something and by asking questions. It's really, I think something in our educational system, I don't know what it is, tells students not to ask questions. And I think we have to somehow tell students that they should ask questions. And I don't know how to get the message through. I used to, in fact, when I do teach in person, I bring bags of candy and I throw candies to students who ask questions. The first question I got, though, was, what kind of chocolate? Because I said I had chocolates to throw out.
Got to be careful what you do there.
He was rather a witty student, rather an amusing student. All right, so I'll say goodbye. And I hope to see you both Thursday at 4 o'clock, and, you know, bring your friends. In any case, I'll record this and put it somewhere, and I'll tell you by email where. So I think I have both of your emails because you've sent me things and so have you. Okay. All right, so I'm going to stop now, stop share. Stay safe, watch out for cars, and stay out of bars. Bye.
Thank you. Bye-bye.
Bye.